Hey, welcome. Today, we are going to decode one of the most fundamental skills in all of science, balancing chemical equations. But I want you to think of it less like math and more like learning a new language, a language that describes how our entire world is built and rebuilt every single moment.
You know, it's a huge question philosophers have chewed on for centuries. But in chemistry, the answer is a hard, fast nope. And that one single, simple rule, well, it's the key to understanding everything we're about to cover.
So let's start there. Let's dive right into chemistry's one unbreakable rule. This is the bedrock principle for every single chemical reaction in the entire universe.
This is it. This is the law of conservation of mass. And what it really means is whatever atoms you start with, you have to end with those same atoms. Now they can partner up differently, they can form brand new molecules and create totally new things, but they never ever just vanish into thin air or pop into existence from nowhere. This is the whole reason we have to balance equations. It's a way of proving we're following the law.
Okay, so if we're learning a new language, we've got to start with the basics, right? The alphabet, some vocabulary, and that's exactly what this next part is all about. The alphabet of chemistry is, of course, the periodic table. Every element gets a symbol that's either 1 or 2 letters long, and the rule here is super simple and super strict. The first letter is always capitalized. If there's a second one, it's always lowercase. So Mercury is Hg, not Hg, not Hg. It seems like a small thing, but believe me, in chemistry, the details really, really matter.
All right, now let's talk about making chemical words, or what we call compounds. There are basically two main ways this happens. On the left, you've got covalent compounds. Think of this like a friendly partnership, where non-metal atoms share electrons. Then on the right, you have ionic compounds, which are a bit more dramatic. Here, one atom actually transfers an electron to another. This creates charged ions, and it's that attraction that holds them together. So sharing versus transferring, that's the big difference you need to remember.
Now, for a super important spelling rule, these 7 elements right here, they're the diatomic elements. You could say they're a little codependent. When they're all by themselves, they never travel alone. They're always found in pairs, which is why we write them with that little subscript 2. Forgetting this is, no joke, one of the most common mistakes people make.
So how in the world do you remember those 7 elements? Easy. You use this amazing mnemonic. Just remember the sentence, I bring clay for our new house. The first letter of each word gives you one of the diatomics. Iodine, bromine, chlorine, fluorine, oxygen, nitrogen, and hydrogen. It's simple, it's effective, and trust me, it's going to be a lifesaver.
All right, so we've got our alphabet, we've got some grammar rules down. Now we are ready to actually start translating. We're going to take simple English sentences and turn them into the powerful language of chemistry.
We'll start with what's called a word equation, and it's pretty much what it sounds like. It's just a plain English description of what's happening. The stuff on the left, the nitrogen and hydrogen, those are our reactants, and what they make over on the right, the ammonia, is the product. That arrow in the middle just means yields or produces. Simple as that.
Now let's translate those words into symbols. We just learned that nitrogen and hydrogen are both on our diatomic list, so they have to be N2 and H2, and the chemical formula for ammonia is NH3. So that gives us N2 plus H2 yields NH3. But here's the big question. Is this sentence actually grammatically correct according to that unbreakable rule of chemistry we talked about?
The answer to that question is nope, not yet. And that brings us to the main event, the great balancing act. This is kind of like the proofreading stage. It's where we make absolutely sure our chemical sentence obeys the law of conservation of mass.
Let's just do a quick head count here. On the left side, the reactant side, we're starting with 2 nitrogen atoms and 2 hydrogen atoms, okay? But on the right side, the product side, we've ended up with only 1 nitrogen and 3 hydrogens. Uh-oh, the numbers don't match up at all. It's like we destroyed a nitrogen atom and created a hydrogen atom out of thin air. We've got a problem.
So how do we fix this? The rule is we can only add big numbers called coefficients in front of the formulas. We can't change the little subscript numbers. That would change the molecule itself. So let's tackle nitrogen first. We need 2 on the right, so let's put a big 2 in front of the NH3. Great, now we have 2 nitrogens, but that also gives us 2 times 3, so 6 hydrogens on the right. Okay, no problem. To fix that, we just go back to the left side and put a 3 in front of the H2. And 3 times 2 gives us 6 hydrogens. And there it is, the solution. 1 molecule of nitrogen gas reacts with 3 molecules of hydrogen gas to produce 2 molecules of ammonia gas. Now if we do our head count again, we have 2 nitrogen atoms and 6 hydrogen atoms on both sides of the arrow. The equation is perfectly balanced. It respects the law.
You probably noticed those little letters in parentheses on that last slide. Those are called state symbols, and they just give us a little more detail. It's like adding adjectives to our chemical sentence. As you can see, we have symbols for solid, liquid, gas, and aqueous, which is just a fancy word for dissolved in water.
Okay, now for some reactions. Especially the ones that happen in water, there can be a lot going on. But not all of it is really that important. So now we're going to learn a more advanced technique that lets us focus only on the real action.
So take a look at this reaction. We're mixing 2 clear solutions, silver nitrate and sodium chloride, and boom, we form a solid. This equation is totally balanced, but some of the things floating around in that water aren't actually doing anything.
These are what we call spectator ions, and I absolutely love that name. They're literally just hanging out in the solution, watching the real reaction happen from the sidelines. In our last example, the sodium ion and the nitrate ion, they start out dissolved in water, and they end up dissolved in water. Nothing about them changes. They're just spectators. So what happens if we just get rid of the spectators? We're left with this, the net ionic equation. And this right here shows us the absolute heart of the reaction with beautiful clarity. A silver ion found a chloride ion, and they stuck together to form solid silver chloride. That's the story. That's the real chemical change. Everything else was just noise.
So, after all that balancing and simplifying, let's tie it all together. Let's ask the big question, why does any of this really matter?
Here's the bottom line. Balancing equations isn't just some boring exercise to get the right answer on a test. It's a reflection of a fundamental truth about how our physical universe actually works. Every time a car burns gas, or a plant does photosynthesis, or you bake a cake in your kitchen, this unbreakable law is being followed perfectly.
And that kind of leads to one last big idea to leave you with. If every single atom that makes you, all the carbon, the oxygen, the hydrogen, if all of it has existed since the very beginning of time, just rearranging itself over and over for billions of years, from stars to planets to who knows how many different things, what does that make you? Just something to think about. Thanks for joining me.